This is Mr. Pillar, ECET 273, Modern Energy, lecture number 14. We are going to be focusing on modern power systems. This is focused on Unit 2 of the Fardo-Patrick text. Okay, when I am speaking about modern energy types, I'm talking about three basic types, the major systems that are used for electrical energy in the United States today. Fossil fuel systems, which include coal, oil, natural gas, hydroelectric systems, and nuclear fission systems. Okay, so here is a graphic that is put out every year by the Lawrence Livermore National Labs. This is the estimated U.S. energy use in 2011. I'm certain we'll be coming up with a 2012 one pretty soon. This is fresh off the internet. I pulled this this morning. 97.3 quads of energy were estimated to be used in the United States. We'll talk about what a quad is here in a second. I want you to note, though, as we read the graphic, there on the left, the inputs, all the energy types, and then where they go to the outputs on the right. There's a fair share of those energy inputs that are going into the block named electrical generation. Not all of them. Those that aren't going into generation of electricity are going towards heating, cooling, or production costs. Transportation costs. That's where those are at. Alright, so as promised, I told you what I would define a quad. One quad is equal to 10 to the 15 BTU. That translates out to 8 billion with a B. 8 billion, 7 million gallons of gasoline. 293 billion, 83 million kilowatt hours, or here's my favorite, 33.434 gigawatt years. 97.3 quad times 33.434 is equal to 3,253.1 gigawatt years that the United States used of energy in 2011. Okay, so we return back here to the graphic. I want you to take a look there. Electricity generation, 39.2 quads. So roughly 40% of the energy used in the United States goes towards electricity generation. The other 60 is going to heating, cooling, and production costs and energy. Out of that 39.2, 12.6 of it turns into electricity. 26.6 quads of the 39.2 quads that goes into electrical generation is lost, is rejected energy. Rejected energy means loss. So it is lost in heat loss, it is lost in frictional loss, it is lost in resistive drop heat loss. That's a large number compared to what's going in. We end up with 55.6 across the board of all energy that is consumed goes out as rejected or lost energy. We lose more energy in inefficiencies than we use to just create the electricity. We lose 55.6% out of the total, and we're only trying to use 40% to create electricity. The purpose of this is to know that we have a ways to go. So energy loss is a problem, and efficiency does matter. Alright. Alright, so as I said, we're going to start with fossil fuels, talking about modern energy uses. Fossil fuels come in solid, liquid, or gaseous form. Shown here in the bottom right is a chunk of coal that I have here in my office. A little bit of play on the fossil fuel. There's a Psittacosaurus skull for you to look at. So speaking with coal, that's the solid. We use coal or coke. Generally we use coal. Coke is used in steel production, but coal is used extensively. From the previous graphic, there was approximately 18 quads of coal that are used to generate electricity. Oil, it would be the liquid fuels. Derivatives of oil would be gasoline and diesel. Gasoline and diesel mostly used for transportation, but oil is used in production of electricity. More used, and we're talking about 0.29 quads of the energy for that. Natural gas would be the gaseous form. That is approximately 7.74 quads of energy that was used in 2011 to produce electricity. I show here also a graphic of the boiler with the steam turbine and condensate and the circulating pump. We talked fairly extensively last lecture about that system, so I'm not really going to delve into it now, but the energy that we're talking about putting into that steam turbine rotation area to get the electricity out is there in the boiler, and that would be a fossil fuel in this case. Currently, right now, coal is about 40% of energy used in America. Basically what they do, like we described for the Wade plant, it's gravity fed, pulverized coal, and they have forced draft fans that keep the coal in while burning up in the top of the firebox. Then it drops down into ash and is removed and utilized in other production ways, like we discussed. Okay, we also mentioned hydroelectricity. All right, so imagine the same plan. We have a turbine, spins a generator. I don't have any condensers. I don't have any preheaters. I don't have to worry about any of that, but I still have a turbine and a hydro plant. Generally speaking, we have a large reservoir of water in the back. That's our store, and we allow that to flow down through a channeled system to a turbine. If you recall, the steam turbine had a governor, and the governor was there to maintain the speed of the turbine so that we maintain the speed of the generator, so we can maintain the frequency of the electricity pulled off the armature. We have the same issue with a hydro dam, but we don't have a governor. What we have is the capability of angling the adjustments of the blades of the turbine, and it's constantly angling those as water flows through to maintain the speed of the motor, to maintain the frequency. We're talking about 13.7 quads that are used in America today. That's hydroelectric. There are some efficiencies that can be done. Some of these dams have been up for 100 years. We can update and increase the efficiency, but as far as adding more facilities, not really going to happen anymore. We've pretty much dammed all the rivers we have available. Down below here on the right, there's a photo of the Hoover Dam. And we talk about dams being a green alternative. Well, it's partially true. Zero carbon output on that dam as it's running. It's taking that water and running it down. Carbon, however, was utilized to create all the concrete, do all the construction, move all that dirt. So the carbon footprint is not neutral. It's reduced every year that it's in operation, but it is not carbon neutral if you think about the whole life cycle of the dam. Other problems that make it not a completely green method: loss of ecosystem. Look at the Hoover Dam. See that big lake behind it? We call that Lake Mead. That didn't used to exist. We lost all that ecosystem. So it's flooded land. So we're missing that land mass that we had, animals that had that as habitat. Now you also have habitat fragmentation. Let's pretend that Bambi's mom is on the north face and Bambi's now on the south face. They can't get to each other anymore. So we have fragmentation. That's a big if there. But anyways, you do have that loss of ecosystem. We also have a problem of siltation and flow reduction of the river. Rivers are supposed to move silt. With a dam there, the silt builds up at the bottom of the dam, right at the base, right there at that water flow location on the schematic. And that's a problem for the dam. We're building up that flow there. We're building up that mass. That's a filtering issue. But as silt builds up, you could actually end up filling in over time your reservoir and reducing your efficiency of your plant. And all that silt was needed downstream to replenish banks and replenish farmland. We don't use that anymore. I did say we're carbon neutral. However, we're carbon neutral after methane emissions are gone. Methane emissions from a hydroelectric dam come from the decaying plant material that's under the water. There was trees and bushes and grass and all those things that got flooded under Lake Mead. That decaying plant material is now in an anaerobic environment, and in an anaerobic environment, that means there's methane output. Methane output will go for years until all of that organic material is fully decayed, and methane is a greenhouse gas. We also have relocation problems. There were people that were living in that floodplain. They're estimated in the world thus far, we've displaced 40 to 80 million people. And then worst case scenario is failure. What happens if that dam fails? That Hoover Dam breaks, there's a lot of problem downstream. So these are all risks about the hydroelectric problems, or hydroelectric generation. Doesn't mean we shouldn't use them, just means that they're risks. Okay, so now here is the nuclear fission route. I am not going to in any way or form attempt to explain the fission reaction, but know that there's control rods, know that they're radioactive based, generally speaking uranium, and those control rods, through their fission, the splitting of the atoms, causes heat to happen, and then we take that heat, we run it through a heat exchanger, a steam generator, and that steam then goes to a turbine. Turbine has governors on it, condensers on it. There's no economizer because there's no flue to put the chill water through. But we generate just like we generate on a coal plant in a nuclear plant, utilizing the fission just as we used the coal burning in the firebox. There's noted issues, obviously. We have problems with what do we do with the fuel rods when they're done, and how do we deal with that. That is in process of figuring out. There's a lot of policy on that. It doesn't, again, mean that it's a bad system. It just means that it's different with different engineering challenges, and that's what we have to go with the day. So I wanted to close out with one more showing of this slide. Estimated energy use of the United States in 2011, 97.3 quads. I don't want to see that number go up anymore. I want to see the reduction of the rejected energy. And hopefully that's where we will be headed. I don't mind how the mix of energies are used on the left. We don't need to get hung up on modern energy, alternative energy, solar and wind, and all these other things. It is a mix of all of our energies, but it is an engineering problem of getting reducing the rejected energy. So there you go. Thank you very much. Please take your notes and come to class asking questions.